Hey guys, this is our second area between two curves today. And the basic ideas are the same, but before we were like, if there's two curves and one's on top and one's on the bottom, you subtract top minus bottom to get the area between them, which is perfect. But there's like a little twist in some of these, which is like one like this one here in our example, that they're like, these are, usually we have like y equals f of x. And when we do top minus bottom. If the curves are given to us as y as a function of x, we top minus bottom. But here you can see they're given as x as a function of y. And basically, the idea is like there's the top and the bottom curve switch here. Like you'd have to solve this thing for y to do it horizontally to like imagine that it's like top minus bottom, but you can't really solve this for y, not in a reasonable way. This one's even more difficult. So if we have x equals f of y, instead of doing top minus bottom, we're going to do left. Oop, that's not right. We're going to do right minus left. And what I mean is we do the right curve minus the left curve. So this one would be the one on the right, and this would be the one on the left. You just basically think of it like everything is sideways. Instead of doing top minus bottom, we're going to do right minus left. So it's the same trick, except everything is in terms of y now. This is like this one we had x limits and dx's. This one we're going to have y limits and dy. Everything here is going to be in terms of y, everything here is in terms of x. So we can still do the same thing though. We write the area as the integral, and we do right minus left. So that's this 12 minus 12y squared minus 12y cubed minus, and then this one, 2y squared minus 2y. And then it's dy, and then the limits have to be y limits. So again, remember with the top minus bottom, we did the smallest x on the bottom and the biggest x on top, and here we're going to do the smallest y on the bottom and the biggest y. So it's like this y is 0 and this y is 1, so we go from 0 to 1. If I do a little simplifying here, let's see, there's a 12y cubed, or negative 12y cubed. There's 12y squared minus 2y, so it's minus 10y squared. And then plus 2y. So that is, add 1, divide negative 3y to the fourth plus 10 thirds y cubed plus y squared, running from 1 to 0. This won't be that hard. Negative 3 plus 10 thirds plus 1. And then minus, and all up in a 0, and for y I get all zeros. So minus 0. So it's this negative 9 over 3 plus 10 over 3 plus 3 over 3. That is 4 thirds. And that's how you do this. Left, this time it's right minus left when it's in terms of y. You sometimes get an option whether you want to do it in terms of x or in terms of y, and it's not always clear which one you should do. And on my test and on the AP test, if you have an option and it doesn't matter which one you do as long as you do it right. So let's do this one. In terms, we're going to do x equals f of y for this one. Let's look at that. And I'm like, if I do the top minus the bottom from 0 to, I think this is 1. Let's see. When x is 1 here, y is 1. And this one, when x is 1, y is 1. So this point here is 1, 1 for sure. So I'll do this curve. This is like the top curve. So from 0 to 1, if you're thinking about it in terms of up and down, the green curve is on top, but from 1 to 2, sorry, the red curve. I'm going to start that over. If you're looking at this like vertically, like thinking about top minus bottom, I have the red curve on top from 0 to 1 and the green curve on top from 1 to 2, and I don't like that. I like it to be the one curve, top minus bottom, or right minus left, just one if I can do it that way. So if I think about right minus left, I have the green curve on the right the whole time and the red curve on the left the whole time. I'm gonna do it in terms of y then. So the y's go from 0 to 1. And then I do, so this, if I want to do this way, then I got to solve this for y. So this is x equals 2 minus y. And this is x equals the square root of y. Okay, so now I do the right curve, which is 2 minus y, minus the left curve, which is square root of y. I'm going to call that y to the 1/2 because math. Now I can just go right to the integration. So this is 2y minus y squared over 2 minus add 1 divide 2/3 y to the 3/2 running from 1 to 0, which is 2 minus 1/2 minus 2/3 minus, all that stuff is just 0 when I put a 0 in. So let's see, this is 6 over 6, this is 3 over 6, and this is 4 over 6. Well, that's unfortunate. Oh, this is 12 over 6. Duh, dummy. 12 over 6, so it's 5/6. I can't really imagine a situation where the answer to an area question would ever be negative. So if you run into that, you might have done something wrong. And I did another one of these because I was like, we can do it in terms of x as well. I'm going to write what the integral would look like, but I'm not going to actually do it just to kind of conserve time. So I could do this. This was, again, I think of this as being, I would call this in terms of y. That's what I would say when I do it this sideways way, like right to left. If I do it in terms of x, probably maybe with respect to x might be a better way to say that. With respect to x and y. That means like the functions are functions of x, y equals functions of x. So that would just be like this. You already determined this intersection point was 1, 1. Oh boy, that's not how anything was. 1, comma 1. So from 0 to 1, I'm going to do the integral of y squared. Sorry, of x squared dx. That'll give me this area right here. I'm just going to add on this other area, which is the integral from 1 to 2. If I solve this for y now, right, I get y by itself is 2 minus x dx. Then you plug in these numbers, and I did this on my own, and I promise that you get the same thing. This one, it feels like has more like mathy shenanigans in it. There's like more business to take care of when it comes to the after you take the integration. So these ones aren't that tricky. So it's not like one is easier than the other particularly, but often one turns out to be much easier than the other. And this, I think, is going to be one of those cases. So I will do this one in the next. Actually, I'm going to skip down to this one real quick because I want you guys to see how to do this. And then the next one, I'll do these next 3 ones. So actually, let's put this here now. That'll be the next one. So sometimes these curves intersect in more than one place. And when that happens, you have to write 2 integrals. Basically, like let's imagine, well, so we can look at this and maybe figure out which curve is which. Well, this one, I mean, you're going to have to use your calculator to find the intersection point anyways. So what I would do with this is I would graph these 2 things in your calculator. And whichever one you put into y1 is going to be the one that is graphed first. And that's how you can tell which curve is which. It's like not completely obvious, I think, what the first curve is. Like which one is the 1 plus x plus e to the whatever, and which one is the x to the 4th one. So if you're not sure, just plug them into your calculator and see. E to the x squared. I'm plugging my calculator right now. E to the x squared minus 2x, all in the exponent. And then x to the 4th minus 6.5 x squared plus 6x plus 2. graph them, whichever one appears first, which looks like when I graphed it, this one appeared first, and I put that as f of x, so that must be f of x. My zoom is far from perfect, but I can just kind of change that up. So this is f of x here, and this is g of x here. So the point here is that I put this into my y1, by the way, and this into my y2. Is that you need to like be able to figure out which curve is on top, which curve is on the bottom. You need to be able to figure out this intersection point. And that's maybe not the easiest thing ever to do. Certainly not easy to do without a calculator. But given a calculator, you should be able to do it. We have these tricks with the calculator to figure out zeros and intersection points and all kinds of things. So here's what I would do. The sum of the regions is this. I don't know what this point is, but I'm going to have to find it. So what I do is I graph these things in my calculator, and I do the little calculator intersection trick. You get second calc, and you go to intersect, and then you just choose the first curve, the second curve, and the guess. You just get close to that intersection point. So that point is 1.0328. 319, and then 2.4011081. And what you really want is you want to find the area, do the integral from 0 to this number, because that's like right there. This is going to be 1.032, 0 to 1.0328. Then we're going to do top minus bottom, which here is going to be g of x minus f of x dx, plus the integral from 1.0328 to 2, which is where they intersect again, of f of x minus g of x dx. And the trick is that f of x is on the bottom here, that's on the top here. So you have to switch the order of the things in your integral in order to get the right area. If you do it the other way, you'll end up, one of these areas will end up being, if you just try and do it with one integral, one of these areas will end up being negative, and you don't want that. You want both to be positive. So you do this, and there's like a way to do this in your calculator so that you don't ever have to like type in these numbers or these functions again, which I'll be happy to show you at some point. Or you can just write down the whole number like I did and type it in, but that's kind of a pain in the butt. So yeah, the two new things in today's lesson are the when we do this thing with respect to y instead of with respect to x, right, with respect to y. And when if the top and the bottom curves switch with respect to y, with respect to x, and if the curves switch from top to bottom. So I think y'all should check out the other example I'm about to do in the next video. It is a pretty good one, and it won't take that long. So I'll see y'all soon. Bye.